Julio. Thank you as well to the organizers for inviting me. It's an honor for me, actually, and the list of names, other speakers on the list is, it's really an honor to be in the same list. I said to Julio earlier that I think my contribution to this work was coming up with the name weighted relations, which is not, I didn't really think of either, but you know, I'm the native English speaker, I guess. Oh, and Jim. Anyway. So I'm aware we've all just had lunch. I'll try not to keep you awake. If I can, I want to tell you about some very simple, a very simple version of quantitative relational model of linear logic, type lambda calculus, and which, thanks to what JS was telling us this morning, we know for sure can be turned into models of differential linear logic, differential lambda calculus, but I definitely won't go into those aspects. So Marie and also JS said that I would be telling you about the relational model, so I guess I better do that, and or maybe not. Maybe we can just imagine that you know that, and Christine will tell you about the probabilistic coherent spaces. So I guess that's everything. So any questions? All right, so the relational model, which you could say is the simplest categorical model of linear logic, works like this. You already know. A formula is going to be interpreted as a set, some kind of set. And a proof of B from A will be interpreted as some kind of relation, so just kind of set of pairs. More generally, a proof of B from a bunch of hypotheses A1 up to AN will be interpreted as a subset of this product. So it's just a relation, just a big relation, nothing more. And this gives you a model of, whoops, that's doing the wrong thing. This gives you a model of linear logic. So here. Oh, in fact, yeah, I thought something had happened. Yeah, okay. So I want to before. So the clicker took me to the wrong place. This is terrible. So I'm going to use the button. It's all my fault. But I want to put kind of our contribution, if you can call it that, into perspective. I guess all of this started with Girard with the quantitative semantics, which had introduced, among other things, the idea, which you'll see popping up in this talk, of interpreting lambda terms as some kind of power series. The relational model of linear logic is going to underpin everything we're about to do. I'm going to build a Cartesian closed category that extends the relational model and its Kleisli category with quantities. And that particular Cartesian closed category was introduced, I think, by François Lemarche in this paper. So what we contribute to this kind of line of work is a connection between these models and programming languages, so a simply typed lambda calculus with recursion and a generic soundness theorem that we're going to prove. Where this really comes from is the models that we have are very similar to what Thomas introduced with finiteness spaces, which he does much more work there, and the Curtis spaces work to ensure that infinite sums are not needed. We're going to see that infinite sums are going to be needed throughout what we do. And the probabilistic coherent spaces, which are a variant of or a refinement of one version of the model that we will present here, were shown to be an adequate model of lambda calculus, again by Thomas. And there's another piece of work that comes after, which is possibly the most remarkable result in semantics that I know about, really. But that's for Christine to tell you about. Okay, so relations. So we have sets interpreting formulas and relations interpreting proofs. And this is going to be set up in this category of sets and relations. So the objects are sets, the morphisms are relations, composition is relational composition that you know. If you don't know it, we have a problem, but it'll be okay. I guess I'll draw you a formula. And then here is how the formulas are interpreted inductively. So the tensor and the linear arrow are interpreted both using the Cartesian product of sets. So as Julia pointed out in discussion yesterday, this model is very degenerate. So the dual is trivial. So A perp and A will be the same thing. So everything kind of collapses. All the multiplicatives collapse. We have an interpretation of the width, the Cartesian product, using disjoint union of sets. This is a kind of standard thing. And because relations are just subsets of the Cartesian product, Morphisms from x cross y to z are the same thing as morphisms from x to y cross z, which means if you pretend that this thing, which is a Cartesian product of sets, which is also the tensor product from the logic, and this thing, which is the Cartesian product of sets, which is the arrow from the logic, then you see that you have a closed category in the simplest possible way. So we get a model of the multiplicative fragment of MLL. And we have a Cartesian product because this thing here is a categorical product, so we can model the width. So that's how that goes. And that's the relational model of linear logic. If someone knows where this first came into being, like who first put this together and understood it, please tell me, because I'd love to know. Everybody definitely knew about it already in the early 90s. And I remember being a PhD student and somebody saying, oh, the relational model of linear logic. And then you go searching through all the papers and you don't find. So I think this was one of these things that everybody kind of invented at the same time. I don't know. Maybe somebody knows. Folklore, exactly. And I must remember not to press that button. That's a bad button. Okay. I knew I shouldn't have been clever with my slides. Anyway, okay, put that down. Don't touch it. So we know how to interpret the multiplicatives. How do we model the exponential, the bang? And you've seen already. So this is interpreted using finite multisets. So bang of A will be interpreted as the collection of, the set of finite multisets of elements from A. So this is the free commutative monoid on the set A, as JS was saying this morning. So I can give you the comonad structure for this thing. If you have a relation, which I'm calling F because I need R for something else, right? So the little f's will be relations, they're not functions. There are other little f's, you can see them on the subscript of the M, that just means finite. But it's okay, right? It's gonna be okay. So if we have a relation from X to Y, bang of F is going to be the relation that relates multisets of X's to multisets of Y's just by, pointwise, you take these n things and you relate each one to one thing on the right and you put them all together and everything is how it should be. Dereliction, the co-unit, is given by this relation, which just relates singleton multisets to their one element. And the digging, the co-multiplication, is this relation that essentially, if you read it from right to left, is taking the union of a collection of multisets, the union of a multiset of multisets, and giving you back a multiset, right? And we get the Seeley isomorphisms that JS told us about this morning, because finite multisets over the disjoint union of X and Y are isomorphic to pairs consisting of a finite multiset of X's and a finite multiset of Y's. So everything just goes through exactly as you would hope for it to do, and it really couldn't be easier. So that's nice. So what are we going to do with this thing? Well, I got an email from Lionel inviting me, and he said, we want a survey of weighted relational models, brackets, concrete, which I took to mean none of your abstract stuff that you like to waste time on, but I couldn't, here's something that I think is important, because we're going to exploit this a bit. So the finite multisets are the free commutative monoids on a set. And so that works in the category of sets and functions, but because rel is the Kleisli category on set for the power set monad, and because that is a commutative monad, there's a distributive law between these things, which means it's also giving you free commutative monoids on rel, which is nice. Rel is self-dual, so those are also co-free, I don't like to say these things, but they're the comonoids, the free and co-free comonoids. So what we have is a Lafont exponential, whether we care about that or not. A lot of that stuff is worked out in a fairly abstract way in this paper of Hyland and others that I've cited there. But this idea that what we want for our model of linear logic are the free commutative comonoids, or co-free. But what we have is a category where we can switch the arrows around, and so we're just going to build free commutative monoids and get on with it, is going to pervade the construction that we see today, at least if you look at this abstractly. So the Kleisli category for this comonad And I'm definitely not going to call that a co-Kleisli category for two reasons. One is I don't think you should put co in front of people's names. That seems a bit rude. And the other is if you look at Kleisli's paper, it's actually about comonads, which is quite fun. Anyway, this gives us a Cartesian closed category, and so you have a model of type lambda calculus. So how does it work? If you have a term of type A arrow B, you get a relation from finite multisets of A's to B's. And I can tell you concretely how the composition works. It works like this. And the nice way to read this is from right to left. So as if it was the Kleisli composition in the category of the monad. So what this is saying is, suppose I've got an F and a G. I will pick this up. And I'm trying to compose them, right? And I'm looking for, under what circumstances can I get the output N out of this composite? Well, what I do is I look inside G and see what, if I want to get the output N out of G, what inputs might I have to supply there? And then for each one of those, I try and get one of those out of F. And that will demand from me some multiset of inputs. Then I collect them all together, take the multiset union, and we're good. Right? And that's how the composition works. I drew a picture. Here is the picture. It's the same thing, right? So this shows I'm trying to get N out of this composite. G is demanding this multiset of inputs. My goodness. And F is willing to supply those inputs as long as it receives these inputs itself. And so then you take the multiset union of all of those things, and that's how that hangs together. Okay. So to make things nice and easy, let's look at a simple example. So let's suppose we have a base type for the Booleans, and we have the obvious interpretation of that as a set, and we have some kind of constants that we built into our model for interpreting conjunction and negation. And then the term x and not y of type Boolean with two inputs x and y is interpreted as this relation. So if x contains the singleton multiset true and y contains true, then we can get false out of this, right? Because true and false is false, and so on. So you have a little truth table. And straight away, you can see that this formula is invoking x once and y once, and you can see that happening in the multisets on the left. So the model's already a little bit quantitative. So now what I'm going to do is contract x and y to be the same variable. And you end up with this relation, which is the same relation, but the two singleton multisets have been put together with a union operation. And so now you have these four entries. And something that's interesting about this is that this is the term x and not x, but you can see that it might produce the output true. And it does that when it receives, on the left, the inputs true and false as the multiset that is the argument x. And so something is happening, or two things are happening here. One is that there's a bit of quantitative information because we can see that x is being invoked twice by this term because all of these multisets have size 2. And also, this term is perfectly, or the interpretation of this term, is perfectly willing to interact with non-deterministic variables, right? So there's some kind of catering for non-determinism going on already, which we're going to exploit. So these are my three remarks. I find it natural to read these relations from right to left. We can already see some quantitative stuff going on, and we can handle non-determinism. So why not? Let's just do that. We can take our term language and add a non-determinism construct to it. This is a non-deterministic choice. And of course, you can just interpret that using union of relations, that kind of thing. All right. So that's the relational model. It's very simple, doesn't tell us much. It's quite degenerate. You can do a lot with it, and you can discover it in lots of different abstract ways. And it's kind of everything's good. It's a great example to have in mind. And all we're going to do to this thing is switch from speaking of sets and relations to speaking of sets and some kind of matrices that replace the relations. So what does that mean? Well, you can think of a relation like this as a matrix, indexed by the sets x and y, and containing Booleans, right? So it just contains a true at position x, y if you want x, y to be a member of this relation. So that's the end of that. Once you do that, I think you either know this already or it's trivial to convince yourself that relational composition is nothing other than matrix multiplication, where instead of the usual times, you use Boolean conjunction, and instead of summing, you take disjunction, and away you go. So the relation G composed F will relate X to Z if there is some Y such that F relates X to Y and G relates Y to Z. That's it. So the ingredients that make this go are we have a binary or finite multiplication operation, we have some kind of infinite disjunction, infinite sum operation, and to make this composition be associative, you need distributivity between the and the or. And that's it. So all we're going to do is take these Booleans, there they are, and replace them by some quantities from some other algebraic structure that supports these two operations and has a distributive law. So what Thomas did with Curta spaces is to work hard to guarantee that the infinite sums that he needed to make these constructions go through would converge. What he did with finiteness spaces was to work hard to guarantee that this infinite sum was in fact a finite sum, because there are only finitely many places where things are non-zero. And what we're going to do is none of that. We're just going to go, let's just assume everything converges and it's all fine, right? What you need for something like that is a structure called a complete semiring, which looks like this. It's a collection of things, collection of quantities, where you have a multiplication and a multiplicative unit, and you have an infinite sum operation. So you can axiomatize this however you want. I mean, you have to get it right, but there are different ways to do this. So we can just say that we want this thing to be a commutative monoid. This is our multiplication, the finite multiplication operation. And we're going to have infinite summation maps. So for every set X, if we have that many entries from R, we can add them all together, and we're always going to get something. And then you have to make sure that that's commutative and associative in kind of obvious ways. And then we ask that there's a distributive law between the multiplication and the summation, and that's that. So kind of very, very straightforward. And so you automatically get a 0, for example. The empty sum gives you a 0 which is a unit for the summation operation. So it is, among other things, a semi-ring. So a rig, if you like, a ring with no negatives. We need these infinite sums. So again, JS pointed that out this morning. As soon as you want to work with these bangs, they are necessarily infinite things. And unless you're going to work hard to get rid of the infinite sums, they're going to be there. So you've got to do something about them. And our approach is just to say, OK, let's just live with them. So that's that. So we've just taken the easy way out of this infiniteness and letting everything go. Something that's annoying about this approach, however, is that as soon as you have a complete semi-ring, you definitely don't have a ring. So you can't have negatives in complete semi-rings. So we're not going to make much use of this or any, but here's a little proof that shows you that as soon as A plus B is equal to 0, then A and B are both equal to 0, which can be slightly annoying. So 0 is presumably the infinite sum of zeros, which is then the infinite sum of A plus B's, and then you associate those the other way, and you isolate this A by itself, and then you have a whole load of zeros coming after. So everything goes to 0. So if you have a ring, you definitely don't have unless it's true, but you definitely don't have a complete semi-ring. So we're straight away forbidden, really, from using what you might call classical algebraic structures. But we do have a bunch of examples of these things. So the relational model, we already know, using the Booleans with conjunction and disjunction gives us one of these structures. And this will yield the relational model. We can instead use the natural numbers augmented with infinity and multiplication and addition in the way that you would expect. And that just works. You can use the reals as well. And so, if a collection of things has a sum, then that's what the sum gives you. And if it diverges, then you return infinity and everything's all right. Here are a couple of examples that blow my brain up, but they're very useful. Sort of logarithmic things. So you can take the naturals or the reals with infinity and use addition as the multiplication, and then the minimum operation as the sum. That's called the tropical semi-ring, and if there's time, I'll mention something about those later. So when you're working with the naturals, you can just take minimums of your infinite sets, and if you work with the reals, you're going to need to take infima of the infinite sets. So it should be the positive reals, I guess, for reasons of you can't have negatives. Okay, so here's how the construction is going to go. If we have a complete semi-ring, we can make a quantitative generalization of the category of sets and relations. So the objects are going to be sets just like before. Morphisms from x to y are no longer going to be relations. They're going to be matrices, so functions if you like. So they take an x and a y and give you a quantity. So what sits in the xy position, what quantity sits in the xy position. So if the semi-ring here is the Booleans, this just tells you do I or don't I have this pair in the relation? And if it's something else, then it tells you something more. And composition is defined exactly as before. So we take the infinite sum of the products of the f's and the g's indexed how you would expect. The identity will be given by the diagonal matrix. If that's a surprise, then again we should talk. And that's a category. So everything from the relational model is going to lift across to the quantitative version, and all you have to do is make sure you know what you're doing with the quantities, right? So at the level of formulas interpreted as sets, everything stays exactly as it was. The closed structure remains exactly as it was before. Morphism from x cross y to z is just a function taking an x, a y, and a z and giving you a quantity. So of course you can shift the y onto the other side and have your closed structure. The disjoint union still gives you a categorical product as it did before, and everything is hunky-dory. It's all very straightforward. Okay. So I guess from this you can infer how the multiplicatives are interpreted. It's a kind of very straightforward thing. What I'm going to do is focus for a bit on the exponentials, and in order to explain most readily the way the exponentials work, I think it's helpful to take a kind of algebraic viewpoint to start to see these things as power series. So a matrix can be viewed as describing a linear map between collections of x-indexed vectors to y-indexed vectors, right? So these things are modules or semi-modules if you want. You know, you can multiply them by scalars and you can add them together. And a matrix, just like in the rest of algebra, a matrix like this describes a linear map between these things. So it's like the free semi-module or whatever on the basis x to the free semi-module on the basis y. So that's one way of viewing these things. So we've got a matrix view, we've got a view of them as linear maps. We can equally look at them as linear maps in the other direction because there's, nobody cares. And once you're looking at them as linear maps, you can view them as simply as any old function from the basis elements to the vectors, right? So the basis elements on the right, if you like, to the vectors on the left. And I like to read these things from right to left. So we can see one of these morphisms as a function that gives us, for each possible output element y, a vector in r to the x, which we can write as a formal sum like this, a formal linear combination of the basis elements. So this is the thing that I like to read as saying, if you want the output y, you have to supply me some input. You can either supply me x1, and then with weight r1, you can have the output y, or you can supply me the input x2, and then with weight r2, you can have the output y, and so on and so on. So this is kind of my intentional reading of what these things are saying. This makes sense? Slight algebraic shift of point of view. So the reason for doing that is I want to be able to describe with the kind of some level of precision the way in which the exponentials interact with the coefficients. So at the level of sets and relations, there are no coefficients around, so there's nothing to worry about. But now, And the multiplicatives don't do very much that would surprise you, but the exponentials are kind of fun. So we want to make the finite multisets over X into a free commutative comonoid on X. In the right to left direction, that's just saying I want to make it into a monoid. So the underlying set already carries a monoid structure, right? It is the free commutative monoid on X. And what we're going to do is extend this monoid structure to the formal sums. And again, it will be done in the only way that makes any kind of natural sense. So it goes like this. I'm just going to do this by example. Suppose we're working just with the Booleans. So I've got a quantitative relation from the Booleans to the Booleans. And here it's not very quantitative because the entries that I'm interested in are going to be 1. So what this says is that I can give you the output true from the input. So this is in the linear category, by the way, so I don't have any finite multisets there. I'll give you the output. If you want the output true, you can supply me the input true, and I'll comply with coefficient 1. Or you can supply me the input false, and I'll also comply with coefficient 1. So this is a very helpful function that whatever you give it just says true on the right. So that's nice. In the right to left viewpoint, that's a function that, when supplied with true, gives you back this formal linear sum, right? It says you can have true, I will ask for true with coefficient 1, or I will ask for false with coefficient 1. Fair enough. So now how do I lift this to be something from multisets to multisets? So the bang f is going to go from, so f is the thing we've just thought of. The bang f is going to be a relation, a quantitative relation, from finite multisets of Booleans to finite multisets of Booleans. And we're going to define this just by multiplication of these formal sums. So if I am asking for the output true, comma, true, the multiset containing true twice, I know that the underlying little f will give me this little true if I supply it 1.true plus 1.false. And this one here will do the same, right? Because they're both the same. And so now we just multiply these two formal sums, formal linear sums together in the only way that makes sense. So you get the multiset true, true with coefficient 1, the multiset false, false with coefficient 1, and then you get true and false with coefficient 1 and false and true with coefficient 1, and so they add together. And I hesitated whether to write 2 here. I guess you can probably figure that out. So what this is saying, so this is how the exponential will be defined as a functor. And if you think about what it's doing, is it's calculating the number of ways in which this output multiset is related to this input multiset, and there are 2. Because it could be, there are 2 permutations of these things that lead to those things. And that's what's going on. So you can write down a closed formula expression for how this works, but I'm not gonna do that. Okay, so armed with this intuition that our morphisms can be seen as giving you, for each output observation that you want to make, some kind of formal sum of inputs that it might demand in order to create those things, and that we're going to put these things together by multiplication in order to create the bangs. I'm going to show you how the Kleisli composition works, because in the end, what I'm interested in doing, or what we were interested in doing, was making the Cartesian closed category that you get from the Kleisli of the bang, and seeing how to model programming languages in there. So let's look at morphisms from bang x to y, where x and y are just sets. This will associate to every output y a vector of quantities indexed by multisets over x's. So a nice trick now is to regard the x's as formal indeterminates, as variables, and then a multiset becomes a monomial like this. So here's a multiset containing 3 x1s and x2 and 2 x3s, and you can write it as a little monomial like that. So a finite multiset is a monomial like this. So a formal linear sum of those things is a power series over those indeterminates. So here is some kind of piece of LaTeX that is supposed to be representing a power series over these indeterminates. So for every finite multiset over the x's, there it is. I have some kind of coefficient that depends on the y, and that's that. So for every output y, I get a power series over the x's. And what I need to do is show you how to compose two such things. And it's just the generalization of the picture that I drew before. So what we're going to do, if we want to do this via linear logic, is first promote the f so that our, what did I do? So that our f that goes from bang x to y gets promoted to something that goes from bang x to bang of y, and I want that to be a comonoid homomorphism. All that means is I have to preserve the multiplications. So all that means is that the only thing I can do is make essentially an algebra or coalgebra homomorphism. I'm going to take, I've already got something that associates to every y a formal power series. I want to associate to every power series a formal power series, and so I'm just going to make this thing in such a way that multiplication and addition are preserved. So, like this. The Kleisli composition works like this. I've got a f from x to y in the Kleisli category, a g from y to z in the Kleisli category. How do I compose them? For each z, I get a power series over y. Then I can take each of those y's and replace it by the power series over x that f gives me, and then multiply everything out. So example coming. Very small example coming. Okay, so here are an f and a g that both go from bool to bool, but in this Kleisli category. So they each associate to true and false a a power series over the indeterminates true and false. So G is going to do this. For delivering the output true, it's going to ask for either two trues or false twice. So two trues once or false twice. Okay, so this is a formal power series over the indeterminates true and false. And to produce false in this example, I've just written 0 because I don't want to be calculating all day. Then F is going to give us true in response to being given either true or false, and will give us false in response to being given true. So how does the composition go? If I take the composition and supply it with false, I'm going to get nothing out, right, because of just linearity. If I supply it with true, what I need to do is substitute this true here with this one here with the output from F, or the demanded input from F. So I get true plus false squared. So the squared is from this square here, coming down to there, and the true plus false comes from there. And then the two falses here get mapped to two lots of true there. Okay, so you just make the substitution, and then you do the calculation. That we've already done the interesting part. We already worked out that true plus false squared is true plus two true falses plus false squared, and so this is the power series that we get. So this is, I claim, exactly the same as the picture of the relational Kleisli composition that we had before. What this shows in this view is, for the output n, here is one of the monomials from the power series, right? So it's a single entry from the formal sum. And there's no coefficient because in this example, the coefficients are all 0 or 1. So this is a single monomial from there. And then we substitute for each of these variables whatever f was looking for. Substitute whatever f was looking for, substitute whatever f was looking for. Again, I've just taken a single monomial from the power series, a single monomial from the power series, a single monomial from the power series, and then I multiply them together. And multiplication of monomials is the same thing as multiset union in this model. So this picture is kind of one, for just tracing one of the possible entries from the left to the right, or the right to the left, depending on how you read it, whereas this calculation gives you the whole thing kind of all at once. And so this is the way that the coefficients for the bang are computed, and I'm not going to prove it now, but this works. So what we end up constructing is the symmetric algebra, the free commutative monoid, over the module of x-index vectors. So that's the kind of the view that we had this morning. And when we're reading the arrows backwards, this is the free commutative comonoid, and so this is the Lafont exponential. So Lamarche noticed this, that he'd constructed his Cartesian closed category, and all of his maps were linear, but only if you read them from right to left. And so he made the comment that linear logic is in fact collinear, which is kind of maybe not quite true, but there's something interesting happening, because, I mean, I presented this, which is really a kind of simple-minded version of the kinds of models that Thomas produced, that JS was talking about this morning. And you saw in the first talk this morning, the opposite of the category of vector spaces was the model. And here we have the opposite of some kind of category of algebras, I suppose. And this kind of thing comes up all the time. That Engler model paper that I referred to earlier by Hyland and the gang also constructs its models as the opposite of some algebraically constructed category. There's a model of imperative programming that was a relational model of imperative programming, which is again the opposite of the category of monoids, and so on and so on. So this is coming up all over the place, which might be deep and interesting or might just be luck. Okay, so let's look at what these things do when you actually turn them to modeling type lambda calculus, so PCF, programming languages with simple, functional, higher-order programming languages with some quantitative elements. And this is what we wrote up in a paper with Giulio Michele Pagani and Jim Laird. A long, long time ago, in a galaxy very, very close. So we have a model of linear logic. We have the Kleisli category for the bang. It's a Cartesian closed category, so we can model type lambda calculus. So let's do it. We can throw in some base types for the Booleans and the integers. We can throw in some constants with the obvious semantics. So the constant true will give you an output of true with coefficient 1. The constant true will give you an output of false with coefficient 0, for example. And then we can, you can model the simply type lambda calculus because you have a Cartesian closed category and nothing interesting is going on. But in this model, we can do things. We can add relations together, and we can multiply them by quantities. So what does that let us do? Well, it lets us add things together and multiply them by quantities. So, for example, you can interpret non-determinism, non-deterministic choice, just by sum of matrices. So if we work with the semi-ring, this semi-ring of natural numbers where the sum is really addition, then, for example, the program true or true, so this or is not logical or, this is the non-deterministic choice, that gives you the output true from no inputs with coefficient 2. So maybe the semantics is counting how many paths there are for the term that you've written to reach the output that you're looking for. And that's what we're going to prove. So as a general thing, what we're shooting for is a result that says if you take a closed term of ground type and look for a particular output in it, that's going to give you some quantity that you understand. And in this case, the quantity that you understand will be how many paths were there for this to reach that particular output. So if it said 0, it means you can't get there. If it says 2, that means there's 2 ways, and so on. So we can weight our relations, right? We can multiply our relations by quantities. You just pointwise multiply all the coefficients by some value from your semi-ring. So that means we can interpret probabilistic choice if we want to. So supposing we work with the reals rather than the naturals, then fix some probability p, and you can make the probabilistic choice of m and n like this. You multiply the matrix for m by p, you multiply the matrix for n by 1 minus p, you add them together and you're done. And this, couldn't be easier. So for example, this term here would give you the output true with weight 3/4, because you get a half from the left-hand side and then a half of a half from the right-hand side, and you see how this is going.
The fact that p is less than 1 is really because you can't have negatives, right?
So yes, the fact that the p I happen to have written here is less than 1 does matter for this, because this, we have to work with the positive reals, and so that's right. I mean, in fact, I could put any two, positive reals here that I want, and they could add up to more than 1 if I wanted them to, and then you just wouldn't know what it was that you that you were writing down. But yeah, that would be fine. Which raises a point. If you think you're modeling probability, you might think that you want to draw all your coefficients from the unit interval 0, 1, But that doesn't work. And the reason it doesn't work is the kind of quantitative aspect that we saw earlier. So here's a way of looking at this. Here is conjunction of two things, x and y. And this will produce false with coefficient 1 if you give it a true for x and a false for y, but also if you give it a false for x and a true for y. And now if I contract x and y together, what ends up happening with the contraction is that you add together the coefficients. And so this thing ends up conflating the patterns true, false, and false, true, of course, because they're just the multiset true and false. And so this term, x and x, you see straight away that it looks at its argument twice, and you discover that there are two ways for this to produce false from the input true, comma, false. So you get the coefficient 2. So even if what you want to model is probabilistic choice, you still are going to have to use some coefficients that are outside the unit interval, which is slightly annoying. But the good news is that it still seems to be counting the paths, the kind of operational paths through the thing correctly. So that's kind of good. Okay, so what we end up doing is giving a weighted relational model to the type lambda calculus and giving a weighted operational semantics to the type lambda calculus and then proving a generic soundness theorem that connects the two. So you can have a syntax like this. We have at least, the type lambda calculus like that, and we have this choice operator, and we have this idea of weighting a term. So it's just multiplication by a scalar. You type this out and you think to yourself, I don't like calling these scalars little r. That seems really stupid. What do people usually use for scalars? And the answer is this thing, which is very annoying. But anyway, never mind. So you can make this thing, and we're going to make a weighted reduction relation that says this term reduces to this other term with this weight in one step. So how does that go? Like this. So your standard reductions from the lambda calculus just get imported with weight 1. The unit of the multiplicative unit of the semiring. The non-deterministic choice can go left or right, each with weight 1, and this little scalar multiplication will just produce a scalar on the arrow and reduce to m. So all that's really happening is that the thing is, you have an operational semantics where the things reduce exactly as you want them to, then every now and again, with ones everywhere, then every now and again they spit out a little r. And that's what happens. So those are the basic reductions. You then embed that in a full operational semantics, call by name weak reduction, that kind of thing. Nothing exciting. And then we can define the weight of a reduction path. So remember, these little r's come from a semiring, so we can multiply them. So if we have a finite path from some term m to some term m sub n, then we get n coefficients, do we? Yes, on the n plus or minus 1 coefficients on the thing, and you can multiply them together and call that the weight of the path. And then, because we have infinite sums, we can say, okay, if I have a closed term of type integer, and I have an integer that I'm looking for, I can say, define the weight of the reduction of the program m to the answer n to just be the sum of the weights of all of the paths by which you can get from m to n. So if there aren't any, you'll get 0. And if there are lots, you might get a finite value, you might get an infinite value. You can express that if your semiring has the right structure, you can express this as the supremum of something, but it's just the sum of the weights of all of the paths. Okay. So here's a little example which served to confuse me, so maybe you'll be exactly as lucky. So here is a term of type integer, right? So it's producing integers. Either 0 or 1 on the left, either 2 or 1 on the right, and then it's adding them together. This is the actual numerical addition operation, and this is where I got confused when I was typesetting the thing. And this OR is the non-deterministic choice, and this OR is the non-deterministic choice. So we're going to have an operational semantics that says evaluate on the left of the plus first of all, so it's evaluating this guy, and so we have two options. It either goes to P0 or it goes to Q1, and then you carry on. You have two more trees. We're still evaluating on the left of the plus, so this will emit the little p as a scalar on the arrow, and then we've got the 0. Now we've got a 0 plus some stuff, so we have to evaluate the stuff. It's a non-deterministic choice, so again we either go left or right, then each of those either emits a p or a q, then you get some numbers, you can actually add them up. And so if you're interested in knowing the weight of reduction paths from this term m to the output 2, you look at the bottom of the tree and you see that 2 appears here and it also appears here. So you need to add up the weight of this path with the weight of this path. And to compute those paths, you just take the non-1 values, the p and the p and the q and the q, multiply them together, add them up, there's the weight of the path. And in principle, especially once we've added recursion to this thing, these trees might be infinite and you have to work a bit harder, but this is basically the idea. So these guys don't have to be probabilities, and this doesn't have to be the probability of reduction, but if you have that in your mind, then that's kind of okay. All right. And so we wrote that down, and then we proved this theorem. And I mean, it was kind of disappointing because everything just goes through. You don't have to do anything clever. Everything just goes through, which is nice. So for any closed term of type integer, if you're looking for the weight of the path, the weight of all the paths from that term to 0, you can take its weighted relational semantics and look in the matrix at the position 0, and then that will tell you what you wanted to know. And that's it. So that's the kind of thing. That's the generic soundness result which connects these things together. But what does it give us? Well, if we plug in the natural numbers semi-ring with ordinary multiplication, ordinary addition, this counts the number of possible paths. So if you write down, if you don't use your non-deterministic choice operation, then nothing interesting happens, but it just counts the number of possible paths from a lambda term. If you take an ordinary lambda term with some non-determinism, it will give you the number of paths from that term to the finish. If you use the reals and you translate your probabilistic choice like this by plugging in a half and a half on either side, so you have a fair probabilistic choice, then it gives you the probability of reduction to a particular value, and that's just what it gives you. If you plug in something like this, so the tropical semi-ring, it gives you the lowest possible weight of all the reduction paths, and down each path, it's adding up the weights as it goes. So one thing that you can do is to take your lambda, or take a lambda term that you're interested in, a non-deterministic lambda term that you're interested in, let's say, and replace every lambda xm with lambda x dot 1m. Now this 1 is not the multiplicative unit anymore. This is the number 1 that's going to, it's like a tick that sort of says, I took a step, I took some time. Once you've done that, and then compute the semantics of the thing, it counts the number of beta reductions that a term takes to reach the answer. Now, I'm not claiming that you can use this model actually, in anger to compute mechanically the number of beta reductions that something takes. That's not the situation, but the model, that is what the model kind of describes. How am I doing? Yeah, good. Okay, so that's all fine for a very finitary kind of calculus where you just have the lambda calculus and you have non-determinism in these weights, which you can think of as a little quantitative sort of effect. We wanted to model fixed points so that we can have recursion. I want to understand what would happen there. And we took the easy way out, again, because, who wouldn't? So the morphisms in our category are these matrices, and they're populated with quantities from our semi-ring. And what we did was to say, let's just suppose that the semi-ring is continuous, which means more or less what you think it means, that essentially that the infinite sums are given by taking the supremum of their finite approximants, and everything around is continuous with respect to those least upper bounds. And then you have a CPO-enriched category, and you can do all the stuff, and standard techniques, standard adequacy proof lets you interpret recursion and get the same soundness result for that. And there's just really, again, not much to it. But I didn't say at the start of the talk that we needed a continuous semi-ring. I just said a complete semi-ring. And that's because, and I'm not going to explain what's on this slide very well at all, that's because Jim Laird managed to show that you don't need continuity in order to get this result. So any complete semi-ring gives you this result. And he does this in a kind of by exploiting the quantitative aspect of the pure relational model, really, in a very clever way. So what he does is he says, okay, I'm interested in this object here, which is the set of nested multisets. So you can construct this object by saying, okay, start with the empty set and then iteratively compute the collection of finite multisets of that, and then the collection of finite multisets of those, and so on and so on and so on, and take all of those together. So you get essentially trees, right? Sort of commutative trees, something like that, or forests. And you can think of each one of these as describing, if you've got a function that you're interested in computing the fixed point of, you can think of one of these trees as describing a potential set of call patterns, where if it's a multiset with, I don't know, 3 entries, you'll say, okay, let's suppose that means the function calls its argument 3 times, and then recursively, each of those entries will tell you what the next level of recursion's call pattern is. So for any possible call pattern, Jim is able to show you how to compute the kind of recursive approximant, or the approximation of the recursion with exactly that one call pattern, and then you take the sum of all of those, and that turns out to be a fixed point combinator. This is magic, in my view. It's not magic, it's algebra, but it's a kind of, I love this. I think this is really, really cool. So this means that this continuity is not required. Yes, Marcelo. Do I take questions now or at the end? I don't know, I guess I already took one. Now is fine, yeah.
So I imagine this is the following. So you have this Banco monad.
Yes.
You are computing the free bialgebra.
This is the free bialgebra for the Banco monad, yes, exactly.
Uniform fixed point operator.
That's exactly the situation, yes. So what Marcelo knows very well is that this thing, is what's called free bialgebra for the Banco monad, and whenever you have one of those, you get a uniform fixed point operator. And the uniform fixed point operator is unique as well. So it's a nice thing. It's a nice thing. And the reason I wanted to mention it is that I have an inkling that this is somehow connected to a related construction that, I don't mean to mention Thomas again, but Thomas and the gang used to construct a model of untyped lambda calculus in these categories, which is essentially the same thing. We're kind of iterating the application of the finite multisets, but taking infinite sequences as well at each time, which is kind of mimicking the D-infinity construction. And this gives you a reflexive object in these categories. So you have a model of untyped lambda calculus as well. So it's somehow, once you know you have one of these, it's not that surprising that you had a model of fixed points kind of all along, but there we are. So that's kind of what was in this paper that we wrote 11 years ago or something, which I now regard as a kind of a very small little contribution in a kind of a much more important line of things. So I don't know, but I think that Christine Tasson will soon tell us about probabilistic coherent spaces. And there is this incredible theorem that if you take the probabilistic coherent spaces, which you can regard as a refinement of this model, then you get a model for probabilistic PCF that is not just sound, but is also fully abstract, which means sound and complete in a kind of amazing way. And people are still working on these things. So there's a nice paper in CSL by Davide Barbarossa and Paolo Pistone about the tropical version of the model, and they've taken that very seriously and studied its differential structure. It's very nice, and they have some nice connections with generalized metric spaces and stuff. So there's this kind of huge slew of work, and this one little point in the middle where we did everything as stupid as we could and still got a paper in Lix. I don't know how that happened. So there, that's all I wanted to say. Thank you.
Thank you, Guy. So is there any question?
So you said you can get fixed point if you assume you have something continuous. You said you can get fixed point if you have something without the continuity. Do these two ways of doing the thing give you the same fixed point when you have a continuous setting?
Yes, so that's a good question. So the answer is yes. The layered result says that whenever you have a complete semi-ring, there's a unique uniform fixed point operator, and the fixed point operator that we get from the continuous construction is a uniform fixed point operator, and so they are the same. They're the same thing. Yeah.
Okay, thank you.
Yeah, it's very cool.
Other questions?
I have sort of a semi-ring theory question, I guess. So you have now infinite sums. So my question is there a natural setting where you have a complete semi-ring that also has infinite multiplication, and why that might be interesting?
That's a good question. I haven't thought about that really at all. So I don't know. I don't want to, I mean,
Sure.
I could speculate, but I would definitely make more mistakes than I make when I'm actually calculating. So yeah, but why might that be of interest? I don't know. I mean, it's always interesting to think about, I guess, but from a modeling perspective, you could, yeah, okay. That would, yeah, that might be worth. Let's talk about what that might do. That'd be fun. Yeah.
Other questions?
Well, about the fixed points, you said that you have only one fixed point because the exponential is free, but if the exponential were not free, could you expect to have more fixed point or not at all?
So you can have more than one fixed point operator, but only one that has this uniformity condition is the way I understand it. And yeah, I mean, you can construct funny examples where the structure of the semi-ring is such that the sum of an infinite set is not, so this infinite set does have a supremum, but the sum of the infinite set is not that supremum, so you have a non-continuous thing, and then you start to hate life and so on because you make a mistake every time you calculate, but at least I do, but yeah. So then you get more fixed points for sure, but only one uniform one.
I just have another remark about the fixed points. So you are doing this in relations, so weighted relations. You can also, as you know, do it in profunctors, one level up. When you take this kind of fixed point, as you talk about, you get one on profunctors. Because we are two-dimensional, in fact, induces one on pre-shifts. And this is one way to recover what people do with recursive, guarded recursion in the topos of trees. So there is, what I'm saying is there is a two-dimensional version of this that is very interesting, and well, it's nice to explore.
Yeah, cool. Yeah, thank you. That's another thing that blows my brain up, by the way. Then.
Okay, so let's thank the speaker again.